So today we're going to start Chapter 2. So we finished up Chapter 1 yesterday with composition of functions. And now we're going to start to talk about polynomials. Okay, we're going to start by talking about just what a polynomial is, when we graph it, try to understand the general behavior of how many times it can turn. Okay? We already know if you have a parabola, x squared, it has a u shape, it only turns one time. Okay, the amount of turns it takes has to do with the exponent, the highest exponent. And the amount of turns that it takes affects how many times it's able to cross the x-axis. Okay. For example, we know with a line can never cross the x-axis more than once. A horizontal line might never cross it, but all other lines will cross it at most one time. Okay, but with curves, it can be a little different. So let's graph this curve and see how many times it crosses. So we've got 2x cubed minus 3x squared. Minus 3x plus 2. Okay, you start with zoom 6, and we'll see if that's good enough. Yeah, it's good enough. Okay, so this is a very typical cubic function. It's turning 2 times, and it's allowed to cross the axis 3 times. Okay, so it comes up, crosses it, comes back down, back up, and crosses the axis again. Crosses 3 times. What's the y-coordinate for every single point where it crosses the x-axis? Yeah?
It's 0.
0. Okay, if you're crossing the x-axis, you're at a height of 0. So if we were to find, which we will a little later on, find these zeros or find these roots, they all have different x values, but they all have the same y value. Any questions on that? Yes?
So is the number of times the line crosses the x-axis the same as the highest exponent?
Well, it doesn't have to cross that many times, but it could cross up to that many times.
Is that, like, if you have an exponent of 5, it can cross the x-axis up to 5 times?
Yeah, it could. It could.
So it's just the same as the highest exponent?
Yeah, like a parabola. It could cross 2 times, but it doesn't have to. Think of a parabola that's been shifted up above the x-axis and opening up. It's never going to cross it. So that exponent is just the limit as to what could happen, but not necessarily does happen. Okay, what I want to do is show that this factored form is equivalent to the original equation. Well, all we have to do, there's 2 ways we could do that. Algebraically, we could FOIL all this out and see if we get the original equation I started with. Or let's just graph this in y2 and see if it looks similar. Graphing and seeing that something looks similar, that doesn't prove it's the same equation. The only way to really prove that this is the same as the original is algebraically, FOILing or distributing it out. So it's x plus 1 times 2x minus 1. And x minus 2. Does it look like it's the same equation? Yeah, pretty much it looks the same. If you go to second table, you could look at some of the values for x and see what they come out to for y. It looks like they're all coming out the same. But again, that still doesn't prove they're the same. But in this case, I am telling you, they are. Now I want to find the exact solutions to that equation. There's 3 different values for x that would make that equation 0. If you have the original equation, that's going to be pretty difficult to find, okay, the way that is. Writing it in factored form makes it very easy to find the zeros. So you're basically trying to solve when x plus 1 times 2x minus 1 times x minus 2 equals 0. So how could that happen? If you multiply three things together and get 0, what must be true about one or more of these factors?
A equals 0?
Yeah, one or more of them must equal 0. Well, in factored form, it's very easy to find what value of x would make the first one 0. Let's do that. Okay. What value of x makes the first set of parentheses 0? Marina? Negative 1. What value of x would make the second parentheses 0? Yeah, go ahead. 1/2. 1/2. And the third parentheses would be 2. Those are the three answers to that equation. And if we take a look at the graph again, that looks like it's about negative 1, 1/2, and 2. We do have a way we can calculate it on the calculator, and I'll show you that in a little bit. Okay, so the trick to solving this kind of problem would be factoring it like this. How do we factor it like that? That takes a little bit of work. Okay, but I'll teach you how you can do that eventually. So if you find a number, okay, that's a solution to the equation f of x equals 0, that number, comma 0, is called an x-intercept. Because when you plug it in, you get 0 for y. Yeah, another name for it is a root or a 0. Depending on the calculator you're using, you'll see it written differently. If you use a I think TI-83 or newer, okay, and you go to second calc, you're going to see the second option is a 0. If you're using a TI-82, and you go to second calc, you're going to see the word root. Root and 0 are the same thing. And the process for finding a root or a 0 on either calculator is the same. Okay, in fact, why don't I show you how we find a root. Okay, so once you have your graph, okay, we don't need the same graph twice. So just graph it once. And then we go second calc 0. Okay, what we have to do is, comes up, it says left bound. Okay, on the TI-82, it might say lower bound, but the idea is pick a point to the left of the 0 you want to find. We've got to do each one separate if you want all three. Okay, so we pick a point somewhere to the left of where we think the 0 is. Pick a point somewhere to the right. Make sure you don't have two zeros in the same interval we're looking at. Okay, I just isolated one of the roots. And then I'm going to do the guess, which isn't overly important. Okay, and it says negative 1. Okay, that was one of my three roots. And I could do it 2 more times to find the other 2 roots. Any question on how you find a root on the calculator? Okay. So for a linear equation, the root is pretty easy to find. All you have to do is basically set the equation equal to 0 and solve it for x. So you'd subtract b from both sides and divide by a. How many roots can a linear equation have up to? Yep, just one. If it's a horizontal line, it might not have one, but any other line will have exactly one root. Okay, so let's just try finding the root here. So the root is the value of x that when you plug it into that equation, you would get 0. So we set it equal to 0 and solve. Okay, Nick, what's the first thing I would do to solve that? 2x equals negative 3. And my last step?
Divide both sides by 2.
Divide both sides by 2. And there's my root. So if you graph that line, it will cross the x-axis at negative 1.5. And that's the only place. Okay, any questions on finding the root for a linear equation? Those are the easiest type to do. Now we're going to step up 1 degree. Okay, linear it's a degree 1. This is a degree 2. It's a quadratic. How many roots or zeros can a quadratic have? At most. What's that? 2. Okay, it can have 2. And remember, we have a test for finding out how many roots it has quickly. We use the discriminant. Okay, b squared minus 4ac. How does the discriminant tell you how many roots there are? There's 3 different conditions. Anybody tell me one of the 3? If b squared minus 4ac comes out what? Then there's a certain number of zeros. Nick?
If it comes out less than 0, then there's 1. If it equals 0, there's 1. If it's 1 and 0, then there's 0.
Yes. So b squared minus 4ac comes out negative, no roots. Comes out 0, 1 root. Comes out positive, 2 roots. Okay, so in this one, they're asking you to solve this quadratic equation approximately. Okay, up to quadratics, we at least have a way we could solve this exactly. If it factored, that'd be great. If it didn't, we just complete the square or use the quadratic formula. But since they want an approximate answer, the calculator is fine. So we'll do it that way. Okay, if I'm trying to find the roots or find the zeros, what does this equation have to equal? Yeah.
0.
Yeah, it has to equal 0. It has to equal 0. So what I want to do is set it up so that it's 0 equals. How could I do that? Yeah?
Subtract 2x squared.
Yeah, you could just subtract 2x squared from both sides. Plus 1. Or you know what? Let's write it in descending order. So negative 2x squared minus 2x plus 1. Right, now, when we plug it in this way, we're finding roots or zeros. If you did it this way, and you plugged one side into y1 and one side into y2, you could do it that way, but you wouldn't be looking for roots. What would you be looking for if this was if 2x squared was in y1 and 1 minus 2x was in y2? Yeah.
An intersection.
You'd be looking for the intersection. Either way you do it, you're going to get the same answer. Okay? Whether you find an intersection between the parabola that's 2x squared and the line 1 minus 2x, or you put everything on one side and calculate the roots. It doesn't matter. Okay. So let's, since we're talking about roots, let's do it the bottom way. We'll plug it in and find the roots. Okay, so it's negative 2x squared minus 2x plus 1. Try zoom 6 and we'll see what we get. Yeah, that's good. And now we'll find the 2 roots. So second calc, 0. Okay, I'll do the one on the left. If somebody else can get the one on the right, that'll be helpful. So pick a point to the left, pick a point to the right, and do the guess. So one answer is about negative 1.37. Okay, negative 1.37. Okay, and how about the answer, the other root? Anyone think they have the other one, Silvio?
I got 0.36.
0.36?
Yeah, 0.36.
Okay, anybody else get 0.36? Get that? Okay. So those are the approximate roots to that equation. Any question on example 2? So one way that they used to try to find the roots graphically, okay, and this is the old way of doing it, we don't do this anymore, is by zooming in. Okay, older calculators like the TI-81, okay, before the one that you're using, didn't have second calc 0 or root. So the only way to find the roots was to use zoom, okay, because they did have a zoom feature. Go over to the root, zoom in, and now I can see, well, it's less than a half, so I can't really tell though because I don't have enough tick marks. So they'd have to add more tick marks on the screen. And now I can tell my root is somewhere between 0 and 0.5. And what you'd have to do is keep zooming in and then making the tick marks spaced closer and closer until you could finally narrow down where it was pretty accurately. So that took a long time. Okay. Now we don't have to do it this way. Okay. We don't have to do it this way anymore. Okay. A better way is the way I just showed you. Second calc root. And by zooming in, you never really got as exact of an answer or as quickly as the method that we can use now. Okay, it may take you 4 minutes to keep zooming in and trying to trace exactly where it was. All right, so let's try this one. X cubed plus 2x equals 1. This is a cubic equation. So how many roots can a cubic equation have? Josh? Yeah. Up to 3. Since it says solve approximately, we'll graph it, and we'll do it that way. So it's x cubed plus 2x equals 1. Let me show you how we can do this one as an intercept. If I was going to do it as a root, I'd subtract 1 from each side and graph x cubed plus 2x minus 1 equals 0. Okay, but I'm going to do this as an intersect. If somebody else wants to try it as a root to see if they get the same answer, you could try that. So we have x cubed plus 2x. And we have 1. Just remember, we're not looking for roots here, we're looking for where they cross. Okay, if you have the TI-84 and you have the application for inequalities, you can just press alpha and then F3 or F4 and you're done. The answer is 0.45. If you don't, you have to go second calc, intersect, first curve, second curve, and take a guess. 0.45. Did anybody try it as a root and get the same answer? Try it? Yep, you get the same.
What were the y values you put in to the calculator to get that?
The function, I put x cubed plus 2x in y1 and then 1 in y2. Those were the two equations I graphed. Yes? You got 0.45 as a root? Yep, so you get the same thing. 0.45. And this is a problem where we've only got one answer. A cubic doesn't necessarily have to turn 3 times. In fact, this one doesn't. Right? It does do something right in here. Right? And in calculus, you'll learn more about that. It switches concavity. Okay, the bottom part goes from being kind of curved downward, and the top part is curved more upward. Right? So it switches its curvature in here. That's not really something we're concerned with at this point, but it's something you'll study more next year. Any question on that? All right, so now we'll summarize a little bit about third-degree polynomials. That's the general form of a third-degree polynomial. A, B, C, and D can be any value you want, any real number, except A can't be 0. If A is 0, you just wiped out your cubic term. Now you don't have a cubic polynomial. Okay, on page 80, they show the 4 basic types of cubics you can have. Cubic polynomials always have a range of -infinity to infinity. They go up forever and down forever. It's just a matter of which end is going up and which end is going down. So in this example, the right end is heading towards positive infinity, the left end towards negative infinity. In this example, it's just the opposite. The left end is heading upward forever, and the right end is heading down forever. This is similar to the last problem. It switches concavity, but it doesn't really turn back on itself. Okay, the other two on the right, they do. They do all the turns that a cubic can take. And if your x-axis was right there, you'd have 3 roots. Okay, so next, I don't want to know the solutions. I just want to know how many it has. Do we have a quick test for looking at a cubic and determining how many times it crosses the x-axis? Or did I teach you it? Marina?
Use the discriminant.
Well, what kind of equations can we use the discriminant on? Only quadratic. This is cubic. So no, we don't have a quick way of telling how many times this crosses the x-axis. Is there a formula to do it? Sure. There's a formula to do everything. But we don't have the formula for doing it with a cubic. So we'll just graph it. So x cubed minus 5x squared is it plus 6x minus 1.
Do you want to change the plus sign to minus sign between the x cubed and the 5x squared?
Oh, did I leave it as the old problem?
Yes.
Yeah, thank you. X cubed minus 5x squared plus 6x minus 1. Okay, it's already equal to 0, so we are going to find the roots. We're not looking for an intersect because I don't have another graph on the screen. Okay, how many roots does it look like that one has? How many, Nick? 3. Yep, has 3 roots. Okay, now I want to actually find one of the answers. We'll find the middle root. Okay, so when I say the middle root in a cubic, I mean the one that's in the middle, not the one all the way on the left or the right. Okay, so second calc, oops, 0. Okay, pick a point to the left, to the right, and the guess. My right boundary was a little too close to that other root. If you grab 2 roots in the same boundary, depending on your guess, you could get an answer that you're not looking for. You could get the wrong root. Okay, but I think I got the one I was looking for. 1.55. Okay. Anybody else get 1.55? Yeah, okay. All right, so 2.1 is basically a quick introduction to basic polynomials. Okay, we're going to study usually up to like 4th or 5th degree, looking at the roots. We generally don't get too much more complicated than that for most problems. Okay, so last part we're going to look at today is the first half of 2.2. And it has to do with finding complete graphs. So some of this we've already kind of done as we've been going along. How do we zoom? How do we find the difference between a window that shows the problem situation versus a window that shows all the important algebraic features? So let's start with this. Okay, so Bill has $20,000 to invest. He's going to invest this money in two different types of accounts. One account pays 6.75% interest, and we're going to do simple interest to avoid issues with compound interest. Okay, so we'll just do simple interest. And then he's going to invest the rest of the money at 8.6%. Okay, so it's two different accounts, two different interest rates, and he's going to invest in some amount of money in one, some in the other. Okay. What would we do if he invests, say, X dollars in one account? How much does he have left to put in the other account based on his total and the fact that he invested X in one of them? Sam?
20,000 minus X.
Yeah, 20,000 minus X. Okay, so that's going to come up. That's going to be important. Okay, the formula you need to use when you're working with simple interest is I equals PRT. I is the interest that you make. P is the principal. Principal is how much money you're investing. R is your rate, and we always do the rate as a decimal. So if he was making, say, 12% interest, that's 0.12. Okay, so we're going to have to convert these percents to decimals. And T is the amount of time that the money's invested for. And we're going to be doing it in years. So first thing I want to do is find an algebraic representation of the interest that he's going to earn in 1 year. I'm going to find an equation that represents how much interest he's going to earn in 1 year. And what this formula is going to do is it's automatically going to take into account if he invests a certain amount at 6.75 and then the rest at 8.6. But there'll be a variable for that. So we can find different interest amounts. Okay, we're going to start and assume that X dollars is invested at 6.75% interest. Okay, so let's start by just calculating the interest he's going to make in that one account. Okay, we'll worry about the 8.6 later. Let's just find the interest on the 6 3/4%. Okay, what's the amount of money that is going to be invested at 6.75? About Andrew?
Could you go back up?
So everything you need is right on that screen.
X.
Yeah, he's going to invest X dollars at 6.75. Okay. How do we write 6.75 as a decimal? Marina?
0.0675.
Okay, 0.0675. And what's the amount of time that we're going to invest this for, Brandon? 1 year. Since we're multiplying by 1, it's not really necessary in this case. Right, so he's going to be making 0.0675x. That's the interest at 6 3/4%. Okay, now let's find the interest at 8.6%. Okay, how much money is being invested at 8.6%? Michael?
20,000 minus X.
20,000 minus X. 1,000 minus X. So there's my principal. What about my rate? 8.6% as a decimal. Tahina? .0,
Yeah, 0.086.
yep, 0.086 is my rate. And my time, again, it's the same amount of time as we had before, 1. All right, so let's do this out. Which property do I have to use to simplify that? Yep, Carly?
Distributed.
Distributive. Okay, times 1, that's not going to change anything. Okay, but we do need to do that out. So we get negative 0.086x. And then I need 20,000 times 0.086. It's 1,720. Okay, so that's how much interest he's going to make in the other account. Now, what would we do with the two expressions I have in boxes to find the total interest? Yeah, Cassie?
You graph them both on the intersection?
Yeah, we're going to. Well, that would give us where he would basically how much money that would have to be invested, so the same amount of interest is made in both accounts, which could be a question we want to know. But for now, we just want to know the total interest from the first account and the second account. So think, what do we do when we total? Shannon? Yeah, add them together. So the total interest is going to be 0.0675x plus the interest that's made in the other account, negative 0.086x plus 1720. Okay, we can combine like terms. So 0.0675x minus 0.086. Okay, so it's negative 0.0185x. So that represents the total interest. Any question on that? Okay, so that's what they were looking for. Find an algebraic representation for the interest in 1 year. Okay, it's right there. Just remember that x is the amount of money that's invested at 6 3/4%. Okay, so we're going to come back to the situation. We're going to use that equation to solve another problem in a minute. But what's the difference between a complete graph of the algebraic representation versus the complete graph of the actual problem? What's the difference? Yeah, Cassie?
The negatives will be cut out because they would not make sense or anything?
Right. When we're talking about the actual problem itself, negative amount of money to invest wouldn't make sense, and a negative amount of interest wouldn't make sense. Right? When we're looking at the algebraic representation, that's when we're showing all the features of this equation, forgetting about what it represents actually. Okay? Showing the intercepts, showing minimums and maximums if it's curved, and things like that. Okay, so any question on the difference between those two? Okay, so using the equation we just have, I want to know how much Bill had to invest in each account if he made $1,509.10 in total interest. Okay, how would we set that up? Bill earns $1,509.10 in total interest. So where would that go? Michael?
You would just set the equation we got equal by the number.
Yeah. This equation equals total interest. Okay, so we'll take the total interest. So 1,509.1. Set it equal to negative 0.0185x plus 1720. And if we're going to solve it algebraically, we just have to subtract 1720 and divide by the negative coefficient in front of x. Okay, but let's do it graphically. Let's try it that way. Okay, so what I'll do is type in 1509.1 in y1, negative 0.0185x in plus 1720. And Julia, what am I going to do once I graph both of these? I'm going to look for where they do what?
Intersect.
Where they intersect. Okay, so we have a y horizontal line up at 1500. All right, so we've got to set our y max a lot higher than the standard window. Okay. I also don't want to look at negative amounts to invest, so I'll take care of that on the x min. X max is the amount of money we're investing. Is there any maximum that we really should have on the screen? Think about the problem situation. X is the amount of money being invested. Did I set X max at like 1 million?
20,000?
Yeah, where does that come from?
Because that's the maximum amount of money that he has.
That's all he has. So we shouldn't look at any values beyond 20,000. They won't make sense in this problem. Okay, negative interest. Doesn't make sense. We're looking for where he's going to make $1,500 roughly in interest. So let's set our y max up around 2,000. Okay, we'll hit graph and see if we have a good window. If not, we'll come back and fix it. Okay, so the red line represents the interest that he makes. The more and more money he invests in the lower interest account, notice what's happening. He makes less. Okay. So the best way that he could do it would be invest all his money at the highest interest rate. But maybe that account has more risk with it. So you get a higher rate, but you could also lose money, like in stocks. Let's calculate intercept. So it's $11,400. Okay, what is 11,400? In this problem specifically, it's x, but I have to go back and remember what x is. Yeah?
Okay, so your x is your principal amount of money that you've invested. So in your first equation at 6.75%, x is 11,400 multiplied by 0.675, the rate. In your second equation, x is 11,400 multiplied by negative 0.086, and then adding 1720.
Okay, so when we plug it in, that's what's happening algebraically, definitely. But what does this represent in the real problem? So algebraically, Marina just went through and explained what's happening with the 11,400. But this is the amount of money that's going into which account in the problem? Yeah.
6.75%.
Right. This is the amount of money that Bill's investing at 6.75%. Okay. The reason we know that is because way back when we started, assume X is the amount of money invested at 6.75%. Okay. Now, what would we do with 11,400 to find the amount invested in the other account? Yeah, just subtract it from 20,000. So 20,000 minus 11,400. He's going to put the remainder of his money, 8,600, into the 8.6%. Any question on that? So last problem we're going to do, we've already looked at this, I think, in a homework. one point. It says, consider all rectangles with a perimeter of 100 inches. Find an algebraic representation that describes the area of these rectangles in terms of their width. And then I want to find a complete graph of the problem situation. Okay, so we did a problem pretty similar to this already. So there's my rectangle, and it has a perimeter of 100 inches. They want me to write a formula, let's see, in terms of the width. So let's let that be the width. And that side is the same as well. What's going to be the length on the top and the bottom? Okay, keep in mind the total perimeter you have, what you've already used up for the width, and the fact that whatever you have remaining needs to be put on the top and the bottom, and this is a rectangle, so those two sides are the same. Carly? Yeah, it would be 50 minus W for the top and the bottom. Okay, the reason it's 50 minus W is because you have 100 minus W minus W. That's 100 minus 2W. That's the amount of material you have left, and it has to be split equally on the top and bottom. So it's 100 minus 2W divided by 2. All right, so now we can do what they want, which is the area. Okay, using the values we have here, what would be the area of that rectangle? Sylvia? What's the area of that rectangle?
50 minus W.
Yeah, there's my length times W. There's a formula that represents the area of the rectangle. Okay, they didn't ask us to simplify it, but we could write it as negative W squared plus 50W if we distributed it. Now it says to find a complete graph of the problem situation. Okay, problem situation means real world. Okay, don't have any values there that wouldn't really make sense in this problem. Okay, we use W because they asked for width, and W makes a lot of sense. What variable do we have to use when we type it in on the calculator? Yeah, we have to use X. Okay, so 50 minus X times X. Okay, now we got to think about our window a little bit. That's certainly not a good window for this problem. Okay, so remember, X represents our width. Is 0 a good minimum for the width? What do we think? Or should we have it lower? Do we have negative width? No, we can't have negative width. Okay, what's the maximum that a width could be in a rectangle that has a perimeter of 100? Think about it for a second. Carly?
25.
Well, it could be bigger than 25. For example, you could have like 40, 40, 10, and 10.
Also 50.
Yeah, it could go up to 50. The width can't go any bigger than 50, though, because if the width went to 51, you'd have 51, 51. That's 102. We went too big. So it could be up to, but not including 50. Okay, now, Y is going to represent my area. From the problem we've already done, we have a thought of what the maximum area is going to be, which is, we already know it's in the shape of a square. So my maximum area is going to be 25 times 25. You could type that in as a calculation and it would figure it out. If we didn't know that, we would just have to take a guess. And I usually like to set it a little higher anyway. So let's set the Y max at 700. And there's a graph representing all the different possible areas in this problem. Okay, so one thing we could do is use the table. If you press second and then table setup, and put the independent variable on ask. Okay, on a TI-82, let me make sure that that's similar. Second table setup, yeah, same thing. Okay, now go second table, and you can type in any width that you want, and it'll automatically tell you the area. If my rectangle has a width of 10, the area will be 400. It's got a width of 16, the area is 544. Of course, there's our maximum area. As you start to get bigger than 25, your maximum area starts dropping now. If you get smaller than 25, the maximum area also starts dropping. And it's symmetrical. So if we go, say, 5 units above 25, or we go 5 units below 25, it's a parabola that has a line of symmetry right at the line x equals 25. Okay, any question on finding a complete graph? Yes?
If you wanted to find the maximum area that you can have, you would just calculate maximum, right?
Yep. Just second calc maximum. Pick a point left, pick a point right, and the maximum is at 25.001. So it's 25. 25. Okay, when you take calculus next year, there's a much faster way of finding this using what's called a derivative. Okay? What happens when you have a line? Does the slope always stay the same on a line, or does it change? A line, it always stays the same. Okay? That's why in Algebra 1 we study slopes of lines. It's easy. Well, when you have a parabola, the slope is always changing because it's curved. But what happens to the slope at the very top? At the very top of that curve, as it just goes from going up to coming back down, what happens to the slope? What do you think happens? Yeah?
Well, technically it becomes a horizontal line, doesn't it?
Which has a slope of what? So what number specifically does a horizontal line have a slope of? 0. Yeah, 0. So in calculus, there's a operation we can use called a derivative that finds the slope of a curve at any point. Well, if you knew how to take the derivative of this and you set it equal to 0, it would tell you where the slope is 0 in this picture, which is also the maximum. So you'll learn how to do that a little more next year. Okay, any other questions? Okay, so the homework for tonight will cover 2.1 and 2.2. Okay, so on page 82, it's 1 through 5, 8 to 11, 15, 27, 28, 31, 34, 40, and 45. On page 88, it's 5 to 12, 21 to 23, and 31 to 34. A lot of page 88 is graphing, so if there's nothing to show on paper, that's okay. Just write down the window you used, something like that. Okay, and don't forget, tomorrow we have our test on sections 1, 3 through what we did today, the first half of 2.2.